Unit 7, equilibrium. We're on question number 31. Let's go ahead and go there. All right, so you have two NOs plus a Cl2 yielding two NoCls, and the Kc is 2000. According to the NO and Cl, a mixture of NO and Cl2 is placed in a previously evacuated container and allowed to reach equilibrium according to the chemical equation above. When the system reaches equilibrium, the reactant and the products have the concentration listed in the following table. So this is at equilibrium. Okay, this is at equilibrium. These are your values. Which of the following is true if the volume of the container is decreased by half? If your volume goes down, then your concentration goes up, right? More moles per liter because you have less liters. So if we divide this by half, then these concentrations are going to double to 0.1, 0.1, and 1.0. Okay, so these concentrations double. All right, so what is our Q now? Our Q, okay, concentration of NoCl squared products over reactants, NO squared and Cl2. NoCl is 1.0 squared over 0.1 squared times 0.1. So this is 1 over 0.1 cubed. It's 0.1 cubed. Another way of saying that is 1 over 1,000. So when you divide by a fraction, you multiply by the inverse, the answer would become 1,000. Okay? So first of all, Q is equal to 1,000. So you can cancel out A, you can cancel out B. We got to figure out which one it is between C and D. Well, okay. If your Q is less than your K like that, which it is right now, because Q, again, 1,000, K, 2,000, okay? If your Q is less than your K, then your Q needs to do what? It needs to get bigger. If Q needs to get bigger, products over reactants, it needs to increase its product. It needs to increase its numerator. So, the correct answer is D. Okay, Q is greater than 1,000, and the reaction will proceed towards the product. Okay, 32. All right, now we have another one of these, like, it looks like kind of like a Hess's law situation. You have Ag, here's your Ag. All right, you have, you know what, let's make that bigger. We're gonna do your NH3 here, your NH3 here, that's two NH3s. We have your AgNH3 plus, AgNH3 plus. Notice the difference between those coefficients. And luckily you have this and this, they cancel out. So what did we do? We added these two things together, so you have to multiply these two things together. 2.0 times 10 to the 3 times 8.0 times 10 to the 3. Look, that's going to become 16, right? And that's going to become times 10 to the 6. I'm going to make that 1.6 times 10 to the 7. The answer is C. Okay. Let's take a look. Oh, this one's interesting. Okay, this is called an isomer. Notice that both these chemical formulas are the same thing. They're C2H2 Cl2. Okay, that's what is known as an isomer, but it doesn't matter. The diagram represents the equilibrium between two isomers of C2H2Cl2, and the table provides a data collection and an experiment to determine the equilibrium constant Kc at 490. In the second experiment done at the same temperature, but you had 1.0 for Z, which of the following is the approximate equilibrium concentration of Y in the second experiment, and why? Look, they're going to be proportional because they're the equilibrium of the first one. Okay, let's set the equilibrium of the first one. It's going to be, you had 0.8. Okay. Let's do this. K is equal to products over reactants. Yeah. That's what K is equal to. And where am I getting that from? I'm getting that from the equilibrium constant because K is about equilibrium. Okay, it's not about the initial, it's about the equilibrium. Well, look, if I do a second experiment, and this time I used 1.0 for my Z, yeah? My second experiment, I used 1.0 for my Z. What is my X? See, it has to be proportional because both of these things are at equilibrium. Both of them need to equal the K. Now, okay, some of you guys might have trouble with this on a calculator. It's going to become 0.8 is equal to 1.2 or 0.8x. So let me help you and think about these as fractions. 1.2 is 6 over 5. 0.8 is 4 over 5. Yeah? So what do you do when you divide by a fraction? You multiply by its inverse, so you have it's reciprocal. You have 6 over 5 times 5 over 4. These cancel out. Your answer is 3 halves. 3 halves is about 1.5. Look at your answers, A, B, C, D. B is your correct answer. Y is equal to 1.5 because the ratio of Z and Y should remain constant when the reaction is done at the same temperature. That's a cool question, and I really like you practicing that kind of math when you think of things in fractions. That's not always intuitive for students, so try to practice that as much as you can. All right, number 34. You have 2 A's plus a B yield 2 C's. A and B react to form C according to the balanced equation above. In an experiment, the previously evacuated rigid vessel is charged with A, B, and C, each with a concentration of 0.1. Oh, so you had 0.1, 0.1, 0.1 initially. Or 0.01, sorry. The following concentration of the gases at equilibrium at particular temperature. Do you guys notice something? You initially had 0.01, 0.01, and 0.01. So what did you notice? Look at A and B. They both got bigger, yeah? But C got smaller. In other words, when we started with 0.1 of all of them, and then we got to equilibrium, to get to equilibrium, it went towards the reactant side. This is a reactant-favored reaction. Well, if you have more reactant than product at equilibrium, that means your K is less than 1. Okay? All right. If this experiment is repeated at a higher temperature, which of the following best describes the effect of temperature change on the concentration of the gases? Oh, that wasn't even what the thing was asking. Okay. If the experiment is repeated at a higher temperature, which Kc is larger. If Kc is larger, you have much more product and less reactant, right? So A, B, C will all increase. No, A, and B will decrease, but C will increase. A and B will remain constant, but C will increase. No, these are going to go down. There will be a decrease in A. That will be 2 times the decrease in B. That makes sense because that's a 2 coefficient. That's a 1 coefficient. Because A and B react to a 2-1 ratio. That is true. They will both decrease. Okay. Now, if you didn't get that, if you didn't get the part where it says this 2-to-1 ratio, well, look at answer D. Answer D says A should be an increase. No, A should not be an increase because it's a reactant, and we're trying to get more product. If we're trying to get more product, the reactant should go down. So the answer has to be C, just based on them saying A is going to decrease. Okay, let's move on. We're on question number 35. All right, let's clean this up. All right. 2 NOs plus Br2 yield 2 NOBRs, and you have your Kp there, and then you have this. The system represented by the equation above is allowed to establish equilibrium. The initial pressures of the substance are given in the table, so these are initial values. Which of the following explains the system will do as it approaches equilibrium? All right. Products over reactants, so we're going to plug in some values here. This is going to become 80 squared over 10 squared times 2. Okay, 80 squared is 6,400, and then this is going to be 200 down here. This becomes 32-ish. Is that right? Yeah, I guess so. All right. So, but what does that tell me? Q is greater than K then, because K is supposed to be 28. If Q is greater than K, okay, first I got to find the one that says Q is greater than K. This says Q is greater than K. This says Q is greater than K. So it's in between A and D. You know what? Right there, I don't even need to read it. Notice this 10 is not squared, but that 10 is. The correct answer is D. All right, let's take a look at number 36. Okay, the decomposition of HI and at 298 Kelvin is represented by the equilibrium equation above. When 100 torr of HI is added to a previously evacuated rigid container and allowed to reach equilibrium, the partial pressure of I2 is approximately 3.7 torr. If the initial pressure of HI is increased to 200, the process is repeated at the same temperature. Which of the following correctly predicts equilibrium partial pressure? Look, if it's repeated at the same temperature, then it means that the K stays the same. So it says, look, the partial pressure, if the initial pressure of HI is increased, so if we increase this, it says, what happens to this? Well, if that increases, they still have to equal that number. That means I better increase too. They both have to increase so that the K is held stable. So the answer, let's see, let's take a look at the answers. It is directly proportional, not inversely proportional, so it can't be B or D. And you got to see the number. Your pressure went from 3.7, and if your pressure from HI doubled, then your pressure I2 should double as well. So we're going to multiply that by 2, and the answer is 7.4. The answer is C. Okay. All right, 37. Iron 3 plus SCN yields that. Okay, for the reaction represented above, the value of equilibrium constant KQ is 240. From this information, correct deductions about the reaction at 25 include which of the following? The reaction is quite rapid. No, we have no idea whether this is rapid or not. That depends on the activation energy, so I don't know. I don't know that. The product is favored over the reactants. Well, if your K is greater than 1, then you have more products than reactants. That is true, so that's good. The reaction is endothermic. Do we know if this reaction is endothermic? Does it say anything about the heat? No, the heat never changed. So we don't know this either. So the answer is B. 2 only. 38. Okay, now you got this a more interesting kind of Hess's law situation going on here. You have this Fe2 and Fe2. Oh wait, yeah. You have this Fe2 plus on the other side, Fe2 plus on the other side. You're going to have to do this. You're going to have to get this HF to become a 2HF. And you're going to have to get this H plus to become a 2H plus. And for these to cancel out, you're going to have to get this F. I shouldn't use red again. You're going to have to get... you're going to have to get that F and that F to cancel out. But obviously you need to multiply this whole thing by 2. How do you multiply a K by 2? Well, you know how you multiply a K by 2? You have to actually square it. Okay? But here's the other thing. Oh, yeah. Yeah. So you're going to have 2 times 10 to the negative 6, and then you're going to have 1 times 10 to the 6 when I squared it. Oh, these are your two new K values. All right. This is going to become 2 times 10 to the negative 6? No. You're going to multiply it. It's going to be 10 to the 0. So, in other words, your K is 2. Okay. Now, actually, that number doesn't matter. All you need to know is that your K3 is greater than 1. Okay? So, if your K3 is greater than 1, it is thermodynamically favorable, because to be thermodynamically favorable means you want to produce products. Okay, it means the reaction goes forward. So yes, this reaction goes forward because if your K is greater than 1, like it is here, if your K is greater than 1, then it means we produce more products than reactants. So the correct answer is B. That actually gets into spontaneity, delta G, but we'll explain that a little bit later. All right, number 39. Which of the following reaction mixtures at equilibrium would reduce the volumes? Would reducing the volume of the container at a constant temperature cause the equilibrium to shift towards the products? Okay, so you got to remember that volume, if you decrease volume, you want to go to the side with less moles. Okay. So this guy over here has 1 mole and then 2 moles. So this would want to go left. Okay. This guy over here has 2 moles and 2 moles, so volume doesn't do anything to this one. This one has 2 moles on the left side, 2 moles on the right side. So again, volume does nothing to this one. And how am I getting these? Sorry, I'm looking at the coefficients of each example. All right, the PCl5, there's 1 here and there's 2 here. This is moving that way. That's what we wanted. We wanted them to shift towards the product. So notice, oh, shoot. Never mind. Sorry. It's going this way. We're still going to, we're decreasing the volume. Sorry, I lost myself for a second. And then this last one, you have 2 moles on this side and 1 mole on this side. It's going to want to go to the right because now you're finally going lower. You're going to the side with less moles. And if you're decreasing your volume, you're trying to get the one that has less moles. The answer is E. Okay? All right, we're at 40. Now you have this hydrogen gas plus bromine gas yields 2 HBRs, hydrobromic gas. I should say hydrogen monobromide, but whatever. At a certain temperature, the value of equilibrium constant K for the reaction represented above is 2.0 times 10 to the negative 5. What is the value of K for the reverse reaction? Remember, K, okay, if it's delta H, you remember you have to make it negative, but if it's K, now this product now becomes a reactant and the reactant becomes a product. They switch sides. So your K, when you do the reverse, so if you have products of the reactants, right? Well, then if you're going to change that K of the reverse, then you're always going to have reactants over products, right? That's what happened here. So what does that mean? The K of the reverse reaction is 1 over K. Okay, so 1 over 2.0 times 10 to the 5. This becomes 0.5 times 10 to the negative 5. This becomes 5 times 10 to the negative 6. The correct answer is B. So remember, when you flip an equilibrium reaction and you're trying to find the K, you have to take the inverse of the K. 41. At 450 degrees Celsius, 2 moles of each H2, I2, and HI are combined in a 1 liter rigid container. The value of the Kc at 450 degrees is 50. Which of the following will occur as the system moves towards equilibrium? Look, if we had equal values of this, and this, we're going to eventually produce more product because your K is greater than 1. So you have way more product, very little reactant. So more H2 and I2 will form. Those things are going to go down because you want less reactants. You want very little reactants. More HI will form. Bingo. Ding, 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 ding. We don't even need to read anymore, but you can if you doubt yourself. 42. Here we go. All right, I see that delta H is positive. If delta H is positive, then heat is a reactant. So again, think of your your Le Chatelier ladder. Which of the following changes to the equilibrium system represented above will increase the quantity of HI in the equilibrium mixture? We're trying to increase HI. So if we're trying to increase HI, we want to get this to happen. Okay. All right, if I add H2 Well, H2 is over here. Yeah? So if I add H2, that is going to increase my HI. That works. Bingo. But these are multiple choices. So increasing temperature. If I increase temperature, that is your heat. And heat again, because it's a product, you would get the same thing. Yeah, that's going to work too. That's going to make us create more products. Decreasing the pressure. If you decrease the pressure, you have to check the amount of moles. Look, there's 2 moles on this side, and there's 2 moles on this side. Pressure does nothing. Not to this equation, because the moles are equal. So that is not true. The correct answer is 1 and 2 only. That is C. All right, let's keep going. 43. Okay, you know what? I have some problems with this question, and I'm trying to. I don't know really. Okay, the College Board is saying the correct answer is D. I don't agree with this. All right. The dissociation of the weak acid HF in water is represented by the equation above. Adding a 1.0 milliliter sample of which of the following would increase the percent ionization of HF in a 10 milliliters of solution of 1.0 HF? Okay, so I'm thinking this. All right. Okay, so watch. I have this. Okay, the first one, if I'm adding KF is a spectator. So I'm adding 1.0 molar of just the F minus. So, okay, if I do that, I'm doing this, right? The HF will not ionize more, it will ionize less because the reaction in this case has to go backwards. So A, you're wrong. Now, think of what the adding H2SO4 does. If I add H2SO4, again, what am I adding? What am I increasing? I'm increasing this guy. If I increase him, we again look like this, okay? Because we are increasing the right side. So same thing, I'm going to create more reactants that way, not products. So that's not going to ionize. Now, HF, okay, I get it. If I add HF, the idea is it does this, right? But the way it ionizes is based upon its Ka value. So the Ka, yeah, that's not true. Like if you are, so this will not increase the percent ionization. The percent ionization will stay the same. We were dealing with HF in the first place. Now we just have more HF. So it can't be. This will not increase or change the Ka. It'll keep the Ka constant because we were dealing with HF in the first place. That's a ratio of products over reactants. So no, it's not C either. But what the heck is D? If I increase distilled water, I mean, are they saying I'm increasing that? You know what I mean? If then it'll make it do this, and then it'll percent ionize more. Well, this is a liquid. Doesn't that not play in equilibrium? I'm kind of confused. Then if you increase distilled water, am I changing my molarity? If I increase liters of water, then this will decrease my HF. Because if I'm increasing water, my molarity would go down because this would have less HF. So I know it's not A, B, or C, but I couldn't figure out why it was D, and that kind of bothers me. But I don't know. Sorry. Once in a while, I'm going to have ones I just don't know how to do, or I don't know what their logic is on that. All right, number 44. Consider the equilibrium above. Which of the following changes will increase the concentration of that? Okay, we're trying to increase this. If we want to increase that, we have to have this happen to stress the system, okay? If I increase the concentration of OH minus, that means I'm going to increase this guy right there. And then that's not right. This is going to cause that, okay? It's going to cause the right side to come down. That's not what I wanted. Adding 6 molar of HNO3. Oh, this is so good. Some of you guys are looking at it and you're like, wait, there is no HNO3 here. There's no even H plus. But you know what HNO3 does? HNO3 takes away the OH minus. Because when you have an acid and a base combined, they form what? Water. Okay? So So looking at your HNO3 and your OH minus, if you add HNO3, you will decrease the OH minus in your solution, and you will look like this. And then once you look like that, you have to produce more product to get back to equilibrium, which will increase the concentration of this. Yeah, that's a product. So yes, the winner is B, adding 6 molar HNO3. Okay, 45. Okay. High solubility of an ionic solid in water is favored by which of the following conditions? The existence of strong ionic attractions in crystal lattice? No. If you had strong ionic attractions that can't be broken by water, you'd have low solubility. The formation of strong ion dipole attractions, that's good. That does. If you're the ion coming from the salt and the dipole coming from water, hopefully that's strong, so it'll help it dissolve. An increase in entropy upon dissolving, that is really true. You want the entropy to increase because aqueous solutions have much more entropy than their solid salt version. So the answer is 2 and 3 only. The answer is B. Oh, sorry, D.